Hello everyone, my name is Nadezhda Blagorodnova, and today in this poster I will talk about the method to predict luminous red nova outbursts with LSST. This is based on a pilot survey which has recently been published by my student. So first of all, luminous red nova outbursts are associated to stellar mergers, such as the one in VA3 Edmond that you can see here. And these are low luminosity transients, which we mostly can observe within a few megaparsecs from us. The good part is that the progenitors of the sources are generally available in HST data, for example, or another archival service, which allow us to study the evolutionary state of that binary, like years before the main outburst. What we see is that most of these progenitors are located in the so-called Hertzsprung gap. And basically, this is a really quickly transition phase between main sequence and red giant branch when the star really expands really quickly. So this is the fast expansion phase of the primary star makes it very likely that the unstable mass transfer will start. And basically mass will be also lost from the whole system in outflows and also in the equatorial plane of the system. However, this phase is not really well understood, but it's supposed to carry quite a lot of the angular momentum of the binary shrinking further and accelerating the merger. So this phase in the outburst is preceded by this precursor emission, which makes it the progenitor brighter a few magnitudes, a few years before the main peak. So our goal, if we want to study what is going on here, is to actually discover the system years before the main outburst and so-called predict the outburst based on this precursor emission. So this was the goal that we followed in the method that we applied to Milky Way stars. So first of all, our goal was to select yellow supergiants using Gaia data. So first of all, we modeled the location of the main sequence and the red giant branch using like density of stars, so well-behaved Gaia stars without extinction, and we will be to construct a Gaussian mixture model. Then we selected the 3 sigma outliers, which would lie in between the main sequence and the red giant branch as the possible progenitor candidates. And we analyzed their light curves from ZTF data using the G and R band light curves. So this allowed us from 10 million initial sources in Gaia ADR3 to select about 21 candidates that then we observed spectroscopically. So as you can see, nearly most of them are showing enhanced emission in H-alpha, showing that some kind of accretion process is taking place. Quite a few of these stars are reddened B stars, so we would not be surprised by their activity, but the binary scenario is very likely. So in some cases, we see a steady increase in the ZTF optical data. This is Atlas. And in some of the cases, also the mid-infrared data from NeoWise also shows very high activity. So it was very nice to see that our best candidate, which was this one, which really showed nice and smooth increase, we detected around here, and a few months later, it went into outburst. This was associated with a long periodic variable, V521, but then the MAXI detection in hard X-rays pointed as a new X-ray binary in the Milky Way. So in this sense, we kind of predicted the outburst for this binary in here. So the proposal is to actually extend this method into extragalactic scales, and instead of using Gaia, to use HST progenitors, and then the wide, fast, and deep survey to localize this luminous red nova precursor emission, because we will be able to detect precursor in very crowded fields and accurately determine the association with possible HST progenitors, and very accurately determine also any kind of variations in their light curves. And finally, the really deep magnitude of LSST will allow us to detect nearly all possible progenitors for the luminous red nova that are also going to be picked up by other brighter surveys. So these 2 filters a night and other complementary filters allow us to constrain this slowly evolving SED. And over the 10-year survey, about 20 precursors are expected to be found, which also have archival progenitor data, so that we can study both the system before, during unstable mass transfer, and then study the outburst itself. So in this sense, LST will open a whole new window into better understanding this unstable mass transfer in massive binaries. Thank you very much.